Hi, my name is Solomon Chiriot, and I'll be taking you through Introduction to Structured Programming, CIT2103. Welcome. This is Introduction to Programming Basics, and during this particular unit, we are going to learn some few concepts about programming, the underlying concepts before you program or before you start writing program instructions. So by the end of this lesson, we'll have looked at some components of a computer system. We shall get introduced to programming languages. We learn about programming fundamentals and problem solving. So based on a computer system where we are going to program, there are some few items or components that we really need to understand before even we start writing program instructions. The first item is the hardware, which is basically the physical parts or the touchable parts of a computer system, the physical parts of a computer. Any electronic device like the mouse, the keyboard, the processor, memory, and so on, all those particular physical parts fall under the hardware. Software is another important component, and that is where we are focusing actually for this particular class. Software basically refers to the set of instructions that tell the computer what to do, or actually control what happens within the computer. So in case you are doing a particular task, basically you are using software to perform those particular tasks. We also have Liveware, which is basically the users of the computer. So based on hardware, we usually have these particular units, the input unit, like the keyboard, the mouse, the scanners, and so on. We also have the central processing unit, which comprises of the arithmetic logic unit and the control unit. The arithmetic logic unit performs calculations and also performs some form of reasoning, so that based on the calculations or based on the results of the calculations, the computer can be able to execute a particular code or to perform a particular task. We also have the control unit, which ensures that all the hardware performs under some ordered set of logic. We also have the output unit, for example, the screen, the printers, and so on. And we also have the storage unit for handling temporary storage of data and instructions and permanent storage of data. We also have software, as we have mentioned earlier. This is the set of instructions that tell the computer what to do based on how those particular instructions have been written. So we look at software being a collection of several programs, and a program is simply a set of instructions that will always tell the computer to perform a given task. So basically we have two reasons why we have this. We have the first one, where we say that the software will tell the computer what to do and also tell other people what we want the computer to do, especially when you are writing program instructions. Other people can be able to read your instructions and understand what we are doing or what we are coding. We have Liveware. These are basically people. These are basically the people who operate the computers or who use the information generated by the computer. Note that computers process data in order to produce information. This information can be used in different areas or different domains, and therefore any user that uses information that is either in soft copy or hard copy will fall under this particular category. Talking about the processor, which is the central processing unit, this is where the instructions are usually executed. This is also referred or seen or viewed as the brain of the computer. Every time you do something on your computer, the CPU has to perform something. The CPU, for example, we have said that it has the arithmetic logic unit and it also has the control unit. So the CPU must be able to take the action and also consider what to do based on the action that you have performed. So if you click on a save command, for example, the processor is able to check where are we going to save this particular document and so on. So the brain or the CPU itself is able to perform so many instructions very fast. The CPU will retrieve instructions from the memory and execute them. Now, there is a reason why we need to understand those particular basics for the CPU, the Liveware, the software, because we want to write instructions that can be executed within a computer system. The instructions cannot just execute themselves. They need some people to operate or to activate them, so that based on a certain occurrence, somebody can be able to click on the mouse, for example. Based on that click event, for example, something can happen. If you click save, if you press the keyboard, something will always happen based on the instructions that have been written for that particular event. So when we are writing instructions, we have to understand that the computer uses a particular language to understand what the users have done, or to understand what actions the users have performed. If you type something, for example, on the keyboard, there's a language that the computer understands. So basically, the computer language is usually made up of zeros and ones, which we refer to as bits, zeros and ones. The computer will not understand 2, 3, 4, 5, 6 the way we understand as human beings. So the binary language, which is the computer language, is usually a set of so many zeros and ones that mean something to the processor, such that when the processor acquires those particular sets of zeros and ones, it can be able to understand them or interpret them and perform a certain action. So it is important when we are learning computers or even computer languages, it is important that we always remember that internally the computer runs or executes zeros and ones. There's a reason why we talk about this, because we are talking about programming languages. We shall see as we proceed that we usually don't code using the computer language, but always bear in mind or remember that whatever you are typing will always be translated back to zeros and ones, so that the processor can be able to understand. The binary number system, as I have just mentioned, is for the computer. But we also need to remind ourselves that for us human beings, we know 0 up to 9. For us human beings, we know number 0, we know 1, we know 2 up to number 9. The 10 digits, that is why we say base 10, from 0 to 9 we have 10 digits, 0 included. That's why we call it base 10. So that is the language that human beings understand or use every day. You can talk of 1,300, but all those numbers will fall under the base 10 system, which is called the decimal system. For binary system, I think we have mentioned this, it is called base 2 because it only associates zeros and ones. So you can only deal with a 0 or a 1, or a combination of so many of them, so that the computer can be able to perform or execute or perform a task in simple terms. So we have mentioned about machine language or machine language. We shall still come back there. Programming languages, we program so that the computer can perform something. We have mentioned that machine language is that particular language that the computer understands. But is that the language that we are going to use? No. So it is important for us to know or understand the underlying concepts of programming languages. It's important for us to understand them because we don't use machine language to code. So basically, when we talk of programming language or programming languages, we are talking about a set of symbols that we use to write instructions. We can write an instruction, for example, to tell the computer, print a certain document using any of these particular languages. So we have three categories of languages which form what we usually refer to as low-level languages and high-level languages. We have the machine language, which we have said is a combination of zeros and ones. We also have assembly language, which is usually made up of symbols. And we also have high-level language or languages which are usually made up of English-related statements. Why do we have all this? Why don't we use machine language? That is something that we always need to ask ourselves so that we understand the reasons why we have the other two categories, that is the assembly language and the high-level language. Talking of machine language, when it comes to programming, machine language is a low-level language. It is one of the low-level languages, and it is low-level because it has been designed so that it can be easily understood by the computer or simply the processor. When we talk of the computer, in most cases, we are looking at the processor. So it is low-level because the computer will understand its syntax very quickly without any form of translation from that particular language to machine language. It is already in machine language, which is zeros and ones. So basically, machine language, which is zeros and ones, is the natural language of a computer. The way we have natural languages that we use to speak or to communicate as human beings, we have English, we have French, and other particular languages. The same applies to the computers. The natural language of computer is basically the machine language. So we have mentioned this before. The instructions are in the form of zeros and ones, which is binary code, or the binary codes, a combination of zeros and ones. Any other type of language should be translated. That is very true. We shall be talking about translation. We also mentioned that there is assembly language, and I mentioned that it is made up of symbols. It is low level. It is low level because it has also been designed to be loosely understood by the processor, which means that the processor can translate it very quickly and execute its instructions. So the design of this particular language, again, is very close to the hardware platform that you are using. When you talk of hardware and languages, remember we are talking about zeros and ones. Now, when you talk of assembly languages can be easily translated very fast, so that these particular symbols, like add, like subtract, or sub, mult, div, can be translated quickly into machine language or zeros and ones that the computer understands. Add, for example, can be a symbol or a mnemonic for the users to understand. Why do we need this assembly language? Why don't we use the binary language or the computer language of zeros and ones? It is very difficult for human beings to understand thousands and thousands of zeros and ones. We are very prone to making errors. So getting or trying to get an error can take even days for you. Maybe to replace a 0 with a 1, or a 1 with a 0, or to add a 0 somewhere, when you have thousands of zeros and ones on your screen. Now, since we understand English, and these mnemonics or these particular symbols are closely linked to English, then it means it is easier for us as human beings to make corrections, modify the programs, and even improve on what the program does. Now, always remember again that the computer will not understand this language because it is not in machine language. So there is a need to translate. There is a need to translate that particular set of symbols. Load R1, divide X and Y, multiply X, Y, and so on. So there will be a need to translate the set of symbols into a collection of zeros and ones that the computer can understand. That is basically into machine code. So remember, the computer cannot understand any other language, whether you are talking about assembly language or high-level language. The only language that the computer will understand is machine code or machine language, or simply the machine language itself, or bits, that is zeros and ones. So we also have high-level language. This is where actually most of the programming occurs, because it is much more easier even compared to assembly language, simply because most of the instructions are created or written using English-like statements or English-related words, e.g. if, begin, else, while, for, and so on. So it is very easy for human beings to understand. It is very easy for human beings to write programs while they are using high-level languages. Some of the high-level languages include Java, C, C++, Fortran, Visual Basic, Pascal, and the list is endless because there are so many of them, Python, and so on. There are so many high-level languages, unlike the assembly language. Reason is very simple, because human beings tend to understand very quickly the words which are written in this particular language. Again, another reason is, of course, it is very easy for you to make corrections. In case you encounter an error, you can be able to know where the error is very fast, because you can read the code the way you read a story. Though there are different syntaxes for that, we shall be looking at that. So we shall be using one of the high-level languages for this particular class, that is C programming language. Now, while we write programs, while we are writing programs, it's important for us to understand a few items that relate to program or instructions creation. When we are writing code, or when we are writing instructions, we deal with what we call source code. We write what we call the source code. That is the code that you write. You can write, for example, if age is less than 20, then do this and that. So that is what we call source code, where you type in as a programmer. Now, since we are using a high-level language, we require a translator. The assembler requires a translator, the assembly language, that is. We also have high-level languages. They require translators. So it is important, when every code that you write, that is the source code must always go through a process of translation, and that is what we call here compilation. Most of the time, or most languages will fall or will use what is called a compiler. A compiler is simply a translator for high-level languages. It is a type of translator which is related to high-level languages. Now, what happens after translation? We produce, or the computer will produce, what we call the object code or object program that can be easily understood by the processor. That means the processor can easily execute the instructions that have been created under this particular set of object code. During the process down here, or during the process of compiling the source code to produce object code, there are several things that happen. For example, you have the source file, you save your source code, you save it somewhere in the hard disk or in a flash disk or any storage device. We have a translator here, which is called a compiler. which of course will translate the source code to object code. The object code again is saved somewhere in the hard disk or in a storage device. And then we have the linker. We also have the linker, which will link your source code to other library codes or other library files within the computer. It depends on which platform that you are using, because there are so many platforms that are used to code. So most of those platforms, they come with what we call the library code, the library files, which are necessary for a particular program to execute. Then after your object code, of course, has been linked with the library files, the computer will produce the executable file. Now, the executable file is the one now which can execute and perform a task. So if you are adding two numbers, for example, or if you wrote a program to add two numbers and display the sum, then that program should be able to ask you, enter number 1, enter number 2, then you produce, or it produces the summation. So that is, it is important to take note of these three items here. That is, we have the source code, the codes that you write, or the instructions that you write. It is also important to note that for every source code that you write, there must be some compiler or translation or translator that is going to translate the source code into a language that the computer can easily understand or can easily interpret and execute. That is the object program or object code. Three important areas: source code, translation, and object code. Now, talking of translators, at least we now have an idea of what a translator does. The translator will simply convert the source code to object code that can be understood by the computer. So when you are typing your codes using a particular editor, for example, you type your codes, you will need to save that particular source code so that you come up with a source file, and then you can be able to compile, or you can use a compiler to do the translation. Now, most of the time we'll be using the compiler. That's why I'm mentioning the compiler. But there are other translators. So we have three types of translators. The first one is assembler. This one is specifically for assembly language, which basically it will translate or convert the source code that is written in assembly language into object code that can be understood by the computer, or that can be executed easily or interpreted easily by the computer. You also have the interpreter. Which is a high-level language translator. The interpreter, we have the interpreter and the compiler for the high-level languages. The interpreter looks at each line as you type, for example, and then it will be able to check its correctness and translate the line automatically, each line at a time. For the compiler, you can write the entire program, which if it is 100 lines, 10 lines, 5 lines, no problem. You can type your code, your source code, then you save the file, then you can do the compilation. Then during this compilation now, if the program has no errors, the compiler will produce the object code. If the program has some errors, the compiler will identify the errors for you, or tell you there are 2 errors, there are 3 errors in your program. These translators are able to identify errors, or are able to check if your source code fits into a particular syntax. Each language has a grammar, or has some form of grammar, whether you are talking about English or French. There are ways of writing words or sentences within this particular English or French languages. The same applies in programming. When you are writing some code, you must follow a particular syntax. you must follow a particular protocol or rule in how you write these particular instructions. So for the assembler, for the interpreter, for the compiler, all of them are capable of checking or ensuring that the code is 100% clean, there are no errors before they execute. So basically the interpreter will look at each line at a time as you type. Before you go to the next line, it will have translated the first line or the line that you are typing. If there is an error, it will report to you immediately before you continue doing or writing the next instruction. For the compiler, you can write today, you save, tomorrow you continue, and compile another time without the need for checking each line. So it is important to take note of that also. Now, if you look at these three, there's something missing in terms of languages. In terms of languages, we talked about machine language, assembly language, and high-level languages. Those were the three categories. There's a reason why machine language is missing here. Very simple. Machine language does not require translation. It is already in a format or a form that the computer or the processor understands. So there is no need for translation. That is machine language. Next, we look at programming. Now that we know we have languages, we have the translators. Programming is simply an activity. You sit down, you start working on a particular problem, you start coming up with a solution to a particular problem, and of course you start writing codes, you test, you execute the codes, and of course you can say, yes, this code is now working, we can deploy the program. So it is an activity that has sub-activities. It is an activity that even starts by simply even designing or writing in paper some particular flow of the solution. So it's not just writing instructions again. Programming can be seen as as a big activity within problem solving using computers. So basically, in a very simple term, we can say programming is simply writing instructions that can execute in a computer. But we don't just start somewhere or from nowhere and start to write instructions. There must be a problem that we are trying to solve. There must be a problem that we are trying to solve. So it is important for us to note that before you even start writing instructions, you understand what is happening or what is going on so that you can be able to plan on how to come up with a solution for a particular problem that you want to solve. As we are going to be looking at programming, it is important for us to note a few items that we shall be dealing with frequently. We shall be looking at lists of instructions where we can execute, we can write instructions that can be executed line by line, which is sequential processing of instructions, where we have line 1, line 2, line 3, nothing special. Instructions are executed from the first line to the last line. Instructions are executed from the first line to the last line. Nothing special when it comes to sequential processing. We shall be discussing that as we are proceeding with the classes. With this is not very good because we don't want systems that just execute without making decisions, for example. So that is why we have the conditional executions. So when you are writing programs, again, it is important for your program to at least give some form of reasoning. And that is why we have what we call decision making within programming, using things like if age is this, for example, if password is wrong, if the username is wrong, then why should you be allowed to log in to a particular system? So those conditional statements make a system look intelligent or to have some form of reasoning. We also have repetition statements or looping statements. This is very critical, especially when you are dealing with a large amount of data. For example, you want to produce a list of people, you want to produce a list of students, a list of units that are coming straight from the database. So you can repeat or you can loop around the table until there is no more data to extract, and that is why we talk of repeating. So you can repeatedly extract records until there are no more records, or even you can extract records repeatedly where a certain condition has been specified. We also have what is called a stepwise refinement, where it is, while we write these programs, it is important for us to break down the program into smaller pieces. This makes it easier for us to make corrections. It makes it easier for us to read the code, and even for other people in future who are going to read your codes, they can easily understand what your program is doing. So it is important to take note of that. As you are writing programs, break them into smaller pieces that are manageable. Then we shall be talking about functions and procedures, set of instructions that can perform a specific task. Coming from these small pieces, we can create functions or procedures or subroutines, a small piece of code that performs something. These pieces of codes can be called anytime when required without affecting or calling the entire program. So we can reuse parts of these particular programs. At our level, it is important to note that we have two methods we can use or we can approach programming. We can use what is called procedural, and from the just previous section, we have mentioned that we can break a program into small pieces. Breaking a big program into small pieces gives you an opportunity to create procedures that perform tasks. So a procedure is simply a set of instructions, a small piece or a small set of instructions that perform a particular task. Once you break down a big problem, you can have the small pieces, and out of the small pieces you can create a procedure for each piece, and therefore you can have what we call procedures. Each of these, again, we can talk of each procedure performing a certain task, where you can execute from line 1 to line 2, or even you can introduce looping, decision making, and other control structures. We also have another approach, which is the object-oriented approach, which we'll be doing at a later time, where we look at a problem, break the problem into small pieces, which are called objects. And then from the objects that represent real-world entities that we find in a particular domain where the problem exists, we can be able to create or come up with characteristics or attributes plus behaviors for those specific objects. Like if it is a school, you can have a student as an object, a teacher as an object, and so on. And you can have from a student object, you can have first name, you can have last name, admission number, and so on. So you can have several characteristics coming out of that. You can have behaviors or methods for that particular object, like a student, like register, print, exam, and so on. So each object will have its own unique characteristics. So those are two methods. For our case here, we shall be dwelling most on a procedural approach. Now, it is important for us to note that we are solving problems. Each program that we write is meant to solve a problem. whether it is a small problem or a big problem. Problems can come from any side of the world, from your friend, from an assignment, from a problem that you face while you do a particular task, either in school or at home, and so on. So you can come up with a program or a system that solves that particular problem. So you can always come up with a solution that fits a particular domain area. So as we always as we always solve these particular problems, it is important for us to look at the steps that are involved during the process of coming up with the solution. So it is always important, while you are trying to ask yourself several questions about the problem at hand, you need to know how to find the answer, for example, to that particular question that you are asking yourself, so that you can solve the problem. You need to figure out how to perform a given task, so that, of course, at the end of the day, you want to program. And you also need to figure out how to make things work. So yes, you need to figure out how to perform a task, and you also need to figure out how to make things work, so that at the end of the day, you have a product or a software solution that performs a certain task. And of course, at the end of the day, we want solutions which can help the society, which can help people in a particular domain, whether it is the banking sector, the medicine sector, and so on. We have 4 steps that we shall look at here. Polya's 4 steps of problem solving. We have to understand the problem. Very simple. We have to devise a good plan, because we want to solve a particular problem. We need to implement the plan that you have devised in step 2. And we also need to evaluate the solution, so that we have a solution that actually fits to our problem, or that solves the problem, so that we don't have a solution that fits another problem that does not exist, or another problem that we are not dealing with. While we try to understand the problem, it is also important for us to always know what we want. Because if I want a particular output, for example, I will need to understand the kind of inputs and the kind of processes that I'm going to use, so that I can produce a particular output. So while you are trying to understand the problem, always look at the scenario very well, identify what is known and what is unknown. For example, identify the inputs, identify the formulas, identify the outputs, so that you can table them in paper. You have not started programming at all. While you also still, while you are trying to understand this particular problem, as I've just mentioned, it is important to always identify the processing mode, which is the formulas. Always identify the inputs and the outputs. Why do we need these 3 items? We need the formulas to process the inputs to generate the output that is required. And when we get the output, it means we have a solution. It means we have the results, and somebody can be satisfied with what he or she was doing at a particular time. So using this particular approach, it is always very important to understand the problem before you start looking at the processes or even the outputs. So as we have just mentioned in a summary, we have the inputs, we have the outputs, and we also need to identify the formulas, understand the problem. very, very clearly, so that at the end of the day, you solve the right problem. Otherwise, you might be introducing a solution to something that is not existing or has not been tabled. We have step 2, which is you devise a plan, which is very important. Focus here is mainly on designing on how to get the solution. How are we going to reach to this, to the solution? We already know the inputs, we already know the processing, that is the formulas, we have identified them, and we know what we want, that is the output. So we know the expectation of our system. We want a system that will give us the sum of 2 numbers, for example. So it is important for us to create an algorithm, which is basically a set of steps that we follow from start to end in order to reach to a particular end, and of course come up with a solution or produce a solution. So always make sure you are, as you devise a plan, make sure your steps that you are coming up with are very small, so that we don't have a complicated plan. So for the algorithms, we use 2 algorithms. We use 2 algorithms, that is the pseudocodes and the flowcharts. We have the algorithm, we have this particular description of what is an algorithm. Basically, we have said that an algorithm is a step-by-step means of getting to a solution. We have the pseudocode, which is actually a set of English-like statements that have a start and an end. English-related statements. Remember, we have not started programming. Here we are just planning. We also have a flowchart, which is a graphical representation of our solution. A pseudocode represents a solution, a flowchart represents a solution. The algorithm represents a solution. So generally, we talk of algorithms following some logic. Any algorithm that you use, must be logical. The steps must always follow some order. We start somewhere, we go to step 2, step 3, step 4, step 5, so that we don't have a situation whereby the steps are not very clear. We have a situation whereby maybe at step 2, you are talking about output for something that has not been processed. So it is important to note that. Now we have an example of a flowchart. We have said a flowchart is a graphical representation of the steps that we follow. That is a graphical representation of the steps that we follow in order to reach to a particular solution, or in order to solve a particular problem. So in case, in a normal situation, this is a normal life, this is not programming related, or you can still work it out as a program. But in a normal case, a human being, in case you have lost an item, for example, you want to find it, you must indicate that if you are doing a flowchart for that particular case, you must start somewhere. So for starting, we have an oval symbol if you are drawing a flowchart. Each of these symbols have a meaning. Each of the symbols have a meaning. So a start and a stop, they share the same symbols at the end of the day. So you must start somewhere. We have an arrow. We say look for lost item. We also say, we can ask ourselves, did you find the lost item? So you look for it, you keep asking yourself, have I found it? If you haven't found the item, you might ask yourself another question, do I need it? If you need it, you can continue looking for it. If you don't need it, you can stop looking for it and do something else. Then, of course, the process ends. We also have another flowchart which you can actually program easily. where we are keying in two numbers so that we can get the sum and output the sum. So again, we have the symbols, the oval, the slanting rectangle, the slanting rectangle, and the oval. So each of these has a meaning. So we can start somewhere, we tell the user to enter the two numbers, then we process using a formula, then we print out. So when we talk of an algorithm must follow some logical order or must have some logic, it means that we cannot start by saying print sum. Then during the end, somewhere there, we say input number 1 and number 2. That will not make sense at all. So the order must be very clear for our algorithms to be efficient and workable. These are pseudocode. We have said pseudocodes use English-like statements. So this is just like start and stop in a flowchart. Then we have English statements. We can say begin. We can declare the two numbers that we need, number S1, S2, and sum. This could represent number 1, number 2. We can tell the user, or we can say output input number 1, so that maybe users can understand that we need an output that tells users to key in number 1, that is S1. Then we can also say input number 2 as an output. Then we put number 2, S2. We process using the formula. Then we give an output, nothing else. The order is very clear. We cannot start from, we cannot say end, then begin. So the order must be very, very clear. We also have evaluate the solution. We also have implement the plan, which is number 3. Number 3, this is where you code. You sit down and you start coding. You sit down and you write the instructions for those particular algorithms, whether you are using a flowchart or a pseudocode. So you're using a programming language, you implement the plan. The plan is your algorithm. So here you will code a little and test a lot to make sure that your program is giving you the right results. You make sure you evaluate the solution. So after writing the codes, make sure you test. You make sure that if you key in 4 and 5 and you are finding the sum, it gives you 9, so that at least at the end of the day you know that it is giving me the right answer. If you key in 9 and 2 and it gives you 7, it means it is finding the difference. And if the problem was finding the sum, then you know that there is a problem somewhere. So it is always important to check the results, compare the expected results and the actual results. You can do that repeatedly with different numbers. So in summary, when we are solving, make sure you understand the problem, identify the inputs, the processes that are needed to generate the outputs. You make sure you identify the inputs, the processes, and the outputs. And how you get the outputs is based on the processes. So always know there is a relationship between inputs and outputs. We process the inputs to get the outputs. When we are devising a plan, we come up with an algorithm, step-by-step procedure that will give us or lead us to a particular solution. And you can always use a flowchart or a pseudocode, depending on your which area that you are dealing with. Most of the time, you'll find yourself drawing flowcharts. We also have the program. We also need to program using a particular programming language, so that, of course, we can have an automated solution, and we can test and test and test by evaluating the solution. So always test the solution. Don't give out the solution before testing. So as we clear this, I would like you to have some work to work on. You write an algorithm to serve as how to. instructions for some relatively simple task or activity. You can have your own activity. Think of an activity. Think of an activity. You are in the kitchen. You want to prepare a certain meal. Prepare an algorithm. You can use the flowcharts or the pseudocodes to create the steps. If you want to create a flowchart, or you want to deal with a problem of preparing a stew, you can be able to do that. You want to prepare tea, you can write the steps, or you can write an algorithm for that particular case. So you choose a task around 10 to 20 steps in length, and assume you are writing these instructions for somebody who has never done or who has never done that particular task. So never, what we are simply saying here is never assume a particular step. Never assume, put it down, write it down, so that other users who have never done that task can be able to note that particular step. So never assume a particular step or jump a particular step, because you will produce a different algorithm for what you are trying to solve, or other people might understand it differently. So that is the end of our lesson 1, and thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.